So in this video, we talk about one more detection mechanism called as cyclic codes. And under cyclic codes, we come across CRC is one method, that is cyclic redundancy check. Cyclic code is a category under which CRC is one method, and there is one method called checksum method. So these two methods are useful for detecting the error, not for correction. So as per the basic concept concerned, cyclic codes are a special kind of linear codes. As already we have a definition for linear codes, means when you take any two valid code words, if you do XOR on those two, the result is again one more valid code word. If such property is maintained by a coding mechanism, then you can call it as a linear coding technique. But along with that, there is one more property to be satisfied by the cyclic codes, that is when you do shifting on this code words. When you do shifting means right shift or left shift, circular shift. When you do circular shift on this valid code words, the result becomes one more valid code word. So in that way, these codes are designed. So that is a basic property of cyclic codes, in which when I take a valid code word, if you perform circular shift on it, that result is again one more valid code word. So, and if you see this cyclic code notation, so it can be notated with C of 7 comma 4. It is a cyclic redundancy code, CRC, where that numbers indicates 7 indicates total size of the code word, 4 indicates size of the data word. The difference between 7 and 4 becomes the number of bits used for the redundancy or parity. So as per that formula, if you take any two code words you take, let us say second one I am taking, when I am doing right shift on it, then what I am trying to do get is I'm trying to get this one at this end, that we call it as a circular shift. So what you will get is 100 followed by 101, and that is already present in this. Here you observe, if you observe this one, 1000101, so that is a result when you perform shifting on this code word. When you perform shifting, circular shift towards right, if you perform on this code word, it is resulted in 100 followed by 101, which is again part of the valid code word. So this way, this property is held by this cyclic code, cyclic redundancy code. Okay, so now if you get into this one, these all are calculated like that only. If you take any two any code word, any data word, and perform take corresponding code word and perform shifting either at left side or right side, again the result must be coming from the same set, then only it is called as cyclic code. Now the methodology the methodology of this CRC is, at both sides, sender side you have a program called encoder, and receiver side you have a program called decoder. Now what the idea behind this CRC code is, we take the data, and to that data redundant bits are added. Which redundant bits are added means, initially these redundant bits are 0, and after passing this data word and these 3 zeros to the generator, it is going to generate a parity bit or redundant bit. This way, generator job is to generate a reminder or redundant bit. That redundant bit is added to the code word to produce a data word, to produce a code word. Once this code word is produced, it is transmitted, and then after, the job of the receiver is do again same process. Now what we are following here is, we are following a methodology called division. We take a number, we perform division on it, and when you perform division on it, we will get a reminder. That reminder is considered as a redundant bit. So here if you observe, we take a word, data word, which is in combination with the zeros. How these zeros are added, how many number of zeros should be added means, that depends on the number of redundant bits required. Number of redundant bit required is calculated from Hamming code formula, that is 2 power r, which is greater than or equal to m plus 1, where m is the size of the message. So then in that way we can conclude how many number of redundant bits we require. Once you got that redundant bits, what we do is, we combine this data word with this 0 redundant bits and perform division with a specified divisor. This divisor is known to both parties. This divisor is known to sender as well as receiver. Now when divisor performs division on this appended data word. Appended in the sense data word is added with zeros. If you perform division on it, we will get a remainder. If you observe the relation between this remainder bits and the divisor, if divisor is having a size of n, you will get a remainder of n minus 1. You will get a remainder of n minus 1. This way, the generator at encoder will create the redundant bits. Now, what happens at receiver side means, at receiver side, upon receiving this code word, the checker job is to recalculate the same job. Recalculate the same job in the sense whatever is received, this 7-bit code word, 7-bit code word is taken and take the same divisor which is used by the sender and perform the division. Now, when we perform the division, if you get a syndrome value as 0, then accept it. And if you get a syndrome value which is non-zero, then that word is discarded. So this way, the syndrome value is calculated. Syndrome value is calculated by performing division. Both parties should agree on one divisor, and that divisor is useful to detect whether the received code word is corrupted or not. So this way, encoder logic and decoder logic is existed at a CRC methodology. Now, let us see in depth. Now take an example. Now, at encoder side, so what it is going to do is, it is going to take the data word. So here in this example, it is data word, and now we are going with a divisor called 1011. For this example, we have taken one divisor, and this divisor is known to sender as well as receiver. Now, I take the data word, and after by looking into the data word, we can conclude that how many number of redundant bits are required. Now, which divisor we are using? 4-bit divisor we are using. When you are using 4-bit divisor, the remainder size is what? N minus 1. So definitely you will get a remainder of 3. So those many number of bits are added to the code word, data word. Data word is taken and appended. It is augmented with the zeros. This we can call it as augmented data word. It is original data word which is pushed with zeros, which is called as augmented data word. After this, what we do is we do general division only. So take this divisor. Now we take leftmost 4 bits. Leftmost 4 bits are considered. In this leftmost 4 bits, the leftmost bit is 1, then the coefficient is 1, and this 1011 is taken and XORed with the above content. I repeat, if you have a divisor 1011, now we need to take some 4 bits of the augmented data word, and in that last 4 bits, leftmost bits, if the last leftmost bit is 1, then we take coefficient as 1, and this entire is substituted here 1011. Now we do XOR on these two. 1 1, it is get cancelled 0, and 0 0 0 0 1 1 and 1 1 0. And now we got a 3-bit 3-bit remainder as of now. Now what we do is we take 1 0 from this appended zeros here, and now you got a number 0 1 0 0. Now if you observe this one, the leftmost bit is 0. So when leftmost bit is 0, it is smaller than the divisor. It is smaller than the divisor. In that cases, we never go with a coefficient of 1 because it is not divisible. Got it? It is not divisible. That's the reason the coefficient becomes what? 0 here. 0, and we substitute all zeros here. So divisor zeros are all zeros you'll get. And now we do the XOR. And if you do the XOR, you'll get 1 0 0. And still remaining bits are there in the augmented data word. So 1 0 is taken, and now it becomes 1 0 0. Now by observing the leftmost bit of it, it is 1. So that coefficient becomes 1. So divisor 1 is a divisor, that is 1 0 1 1. So again we do the same job like cyclically. So finally we get 0 1 1. Still one more 0 is there that can be appended, and once it is done, observe the leftmost bit, it is 0, so no more division is possible. So what we do is, again we place 0 in the coefficient, divisor 0 is a 0. So this 0 is given here and subtracted. Subtracted in the sense XOR operation is done. So what we got is, we got 1 1 0 is a remainder. 1 1 0 is a remainder. Now code word is prepared by the sender. Code word prepared by the sender is data word which is combined with this reminder. That what is data word? 1001 is data word and the reminder is 110. These two are merged, combined, and that is what sent to the receiver. Okay, this way the division process works at a encoder program of the sender, right? So if you observe at a receiver, what happens? Now division process at decoder means at receiver. Now if it is properly sent, how do you recognize it is correct? And if something is wrong in the transmission, how do you detect there is an error? These two cases are covered here. Now the code word prepared in the encoder program is what? 1001110. This is what. Now what we do, what we do here is we take that code word, see this one, code word is taken and the same divisor we are using, whatever the divisor used by the previous program, that is encoder. Now we do the same process. Now we take last 4 bits of the code word and leftmost bit is 1, so that divisor quotient is placed as 1 and the divisor is placed here and subtracted by doing the XOR. You will get 0 1 0 and take 1 from the augmented code word. So you have remaining bit side, 1 is placed here. So you got 0 1 0 0 1 0 1 and now it is smaller than the divisor. In that case we substitute zeros only by placing quotient as 0. So divisor 0 is a 0. Again you do the XOR, then you will get 101 and take 1 from the code word. Take 1 from the code word, then you got 1011. Now if you observe this part, the leftmost bit is 1. So it is possible to perform the division. It is possible to perform the division, that is quotient is placed as 1 and you got 1011. When you got 1011, if you do XOR, both are same. When both are same, all zeros are appeared and take 0 and when it is 0 again 1011 is the divisor, 0 is the quotient and we place 0. And finally if you do the XOR on zeros again you will get 0. So now at receiver side, if you perform the division by using the same divisor, then you get a syndrome as 0. When you got syndrome as 0, consider that no data is corrupted in the middle. There is no error in the data transmission. This way, the CRC method is going to detect the errors based on the syndrome value. If syndrome value is 0, no errors are detected. And if syndrome value is non-zero, then it is going to indicate that something is wrong. But it is never detect where is that error occurred in the transmission. So that means it is not used for the correction. It is not used for the correction. So this way it is positive case. If everything goes fine, this happens. Now assume a scenario where one bit is get changed in the data transmission. So the original code word is 1001110. And now what is changed here is in code word, one of the bit is changed in code word, one of the bit, that is fourth bit from right and left both. Fourth bit is changed to 0. Now what we do the same process, like take the same divisor and take that code word and start the division, identify the leftmost bit and as it is 1, you can do the division by placing quotient as 1. So 1011, do the XOR, you will get 011 and take 1 from the above and now you got 011 which is still less than the divisor. So we place 0 in the quotient and we place all zeros here and perform XOR, you will get 111 and take 1 from the above, then you will get 4 ones. When you got 4 ones which is greater than the divisor, then coefficient is placed as 1 and 1011 is placed and perform the XOR and it will get 100 and still one more 0 is there in the code word, that is taken out and now it becomes 100. Now whenever it is 100, the leftmost bit is 1. So this divisor again substituted here, the division is substituted here. Actually here it is 1, here it is 1, mistakenly written like 0. 1 is placed and that 1011 is placed, and when you do the division XOR, then you will get a syndrome as 011. When you get a syndrome as 011, then it is a non-zero value which indicates that error is detected and the data word is not considered. This way CRC method will works well to detect one bit errors, to detect single bit errors, and it is not used for the correction purpose. So it is very simple method to understand, and let us look into this again with one more example. Now you take this one, data word is 100 100. When you got data word as 100, the key is nothing but divisor. In some books it is treated as key, divisor, polynomial, generator. These are the different words used for this key or divisor. So now the divisor is 1101 and the data is 100 100. When you got 100 100 as your data, how many number of zeros are added? This depends on the divisor. If you take a divisor of size 4 and number of zeros to be appended is what? N minus 1. If divisor size is n, then the number of zeros to be appended to the data word is n minus 1. So now this time 3 zeros are added and the same process is followed and we got a remainder of 0 1 1 at the end. Same process is followed. When 0 1 1 0 0 1 is your reminder, this is added to this data word. So totally code word becomes what? 100 100 followed by 001. So this way it can be calculated the remainder at encoder. It can be calculated very easily with a taken divisor. So similarly we'll take one more example where you got error scenarios also. Now the received code word. The received code word, let us say code word received at the receiver side is 100 100 001. Okay, 001. So that's what we got in previous. Now when you got this one, a same process is followed by the decoder of this receiver. 1101 is the same divisor, and now this is the code word. Now here we are not appending any zeros because it is already filled with the reminder. It is already filled with the reminder. That's what we have received. So no need to add appended zeros. At sender side, first we need to add appended zeros and later we'll get a reminder. That reminder can be binded with the data word. But now in this case, no extra bits are added because you got already total data word plus reminder. Now we start doing the division by checking the leftmost bit of the code word. If it is 1, then we substitute 1 in the quotient place and this 101 is placed. Perform XOR. Again you got 1 in the leftmost bit. Again quotient is 1. As long as you will get 1 in the leftmost bit, you will get quotient as 1 and the same divisor is taken for the XOR. When you got leftmost bit as 0, then the quotient is placed with 0 and this divisor is not considered for the XOR. 000 is considered. 00 is considered and then you got a result of like this. And if it is as it is having leftmost bit as 1, then the quotient is placed with 1 and the same divisor is taken for the XOR operation. So if you got a result as 0, then nothing is corrupted in the transmission. This is called successful transmission of the code word. Successful transmission of the code word. Now we will see unsuccessful transmission. Now unfortunately there is an error in the data transmission. The received code word, I think it is similar side. Okay, this is error. So now we have received something else. It is for error we have taken one more data word and code word key is this one and we'll got a 001 as a reminder. And now if it is transmitted, whenever it is transmitted, if now the code word to be transmitted is what? 100 100 001. Now what we will do is, as part of exercise, you corrupt any of the bits of the data word or whatever it may be. In that code word you corrupt one bit and you do the same process again, then you will get a non-zero as a syndrome. Non-zero as a syndrome at a receiver. This is at sender side. So receiver side, you just do one practice exercise so that you can understand how this method is going to detect the errors. Okay, if the syndrome value at receiver is non-zero, then there is a problem in the data transmission. That data word is not considered. So this way it works. Now, in order to work with this binary notations, we require all the zeros and ones. So if you are having bigger messages, like here it is okay, you can consider. If you are having very bigger data like 100 bits data, 200 bits data, then it is a little bit difficult to represent that data in the form of zeros and ones. And to avoid it, there exists one notation called as polynomial notation. In polynomial notation, we make use of the equations. We make use of the equations that can be represented with less number of bits as compared to the binary representation. So let me show that slide where you can get a clarity. So now here polynomial representation of that divisors or code words, whatever it may be. Now we got a code word of like this. So in order to represent this one, you must require 7 bits. You must require 7 bits. So instead of writing 7 bits, this can be represented in polynomial in this way. So 1 multiplied by x power. So first one is x power 0, x power 1, likewise it goes on up to x power 6. Wherever you got ones and that is only having value, wherever you got ones that is only having value, and zeros can be skipped away, very simple. Whenever you have 0, that equation not required in this sum. So finally what it becomes is, it becomes like this, x power 6 plus x plus 1. So instead of using 7 bits to represent this divisor or code word, it can be represented in a shorter form when you make use of the polynomial representation, which make use of the equations, where that powers will indicate a position where 1 is appeared, if you observe this one, x power 6 means in sixth place 1 is present. X power 1 at first place 1 is present. 1 can be represented like x power 0, at 0th place 1 is present. This way binary notation can be written in a shorter form with the help of polynomial notation. So we will see some examples on polynomial also. So now the same process what we have deployed for the binary notation, the same we are using, but in the form of equations. So now the divisor, what it indicates, this divisor means 1 0 1 1. So we have skipped one bit because x power 2 is not there, so that is 0. So at third position we place 1, second position 0, first position 1, and 0th position 1. So 1 0 1 1 is the divisor, which is represented with 3 notations. 1 0 1 1 you require 4 bits, but if it is converted into polynomial notation, it is enough with 3 bits, x power 3, x and 1. Okay. Similarly, when you take this one, your data word. Now data word is 1 0 0 1. 1 means third bit is 1. Second and first bits are 0. That's not considered here. X square is not there, x is not there. So both are placed with zeros. And 1 means x power 0. So then the data word, equivalent data word for x cube plus 1 is what? 1 0 0 1. So this way 1 0 0 1 can be easily represented in polynomial with 2 notations, that is x cube plus 1. Now how the procedure begins means, when you start this encoding process at sender side, in previous method we used to upload the zeros at the end, that we call it as augmented data word. Now what we should do in this case means, we take the highest power quantity from the divisor. Highest power quantity is what? X cube. Now this x cube is multiplying the data word, very simple. This x cube is multiplying the data word. Ultimately the positions are moved, very simple. Previously it is x power 3. Now by moving it goes to x power 6, right? So the process of creating augmented data word in polynomial notation is identify the highest term in the divisor, that is x power 3, and multiply given data word with this highest power. So what you will get is x power 6 plus x power 3 you will get. So this is what the preparation of augmented data word. And after that, let us start with the division. Now what is the leftmost bit in this? X power 6. Now in order to make this x cube as x power 6, it should be multiplied by x cube. So coefficient is x cube. So this entire equation is multiplied by x cube to get this one, x power 6, x power 4, x power 3. And once it is done, we perform XOR again. X power 6 get cancelled, x power 3 get cancelled, and we got x power 4. Now as x power 4 is bigger compared to x power 3, again we make use of coefficient only. Coefficient is x this time, because in order to convert this x power 3 into x power 4, it should be multiplied by x. So x power 4, x power 2 and x. These two are get cancelled this time, and now you get x power 2 plus x. Now we got a divisor which is having in its power compared to the divisor. So the divisor is having highest power of x cube, but the remainder is having a power of what? 2. Then what we do is we stop our division process. Consider it as a reminder, and this reminder is appended to the data word to become a code word. So this way the number of steps in division process also decreased. Here zero divisions are not there. Very simple. Zero divisions are not. We never find zeros in the coefficient. We found only one positions, x cube you require, x you require, and we are not bothered about this zeros logic. That's the reason the number of steps in the division process also decreased to a smaller number. This way CRC is going to benefit us in representation of the bits, like a huge number of bits are required to represent this code word, data word or divisor in binary. It can be easily represented in a shorter form with polynomial. That is one. And the division process also cut down to minimum steps by considering only once in the coefficient. So then this is what prepared by the CRC division process in polynomial methodology. Now let us see this one. Now about this decoding process. Now we take this one at decoder side, x6 and x3, all these things are taken, and we start doing division on this code word, received code word by this divisor at receiver side. At receiver side, we make use of this equation to perform division on the received code word, and we do the division until the end. If you get 0 at the end, the received code word is not having any error, and if it is not 0, then you can conclude that there is something wrong in the notations. This way, this method is very useful for us to identify the errors. So let us stop in this video, and in next video we talk about how this divisor is taken place. So always we are taking like just like that, x cube plus x plus 1. So what are the minimum steps to be followed to select a divisor? So those things we will see in the next video.